The next talk is on key homomorphic and aggregate verifiable random functions by Giulio Malavolta. And unfortunately for Giulio, since he doesn't have a co-author, he has to give the talk.
Sorry about that. Thanks, Mohammad, for the lovely introduction. So I ended up making a lot of slides, so I'll get right into it. So this is a talk about verifiable random functions, which are keyed functions that map a set of bit strings to a particular domain. And we require two properties of this function. The first is pseudo-randomness, so that an adversary with oracle access to the function should not be able to distinguish it from a truly random function. This is computational indistinguishability. And in addition, we augment this function with two more algorithms which allow one to prove that an image was correctly computed under a certain preimage. And given the proof, the image of the preimage, one can verify that the proof was done correctly. And uniqueness requires that no adversary should be able to return a tuple that correctly verifies, but the y star does not correspond to the evaluation of the function. So there are many notions in the literature. I think the original paper defined it to be for all adversary and probability being 0, which thereby the name. But you can also relax it for this probability to be negligible and the adversary to be efficient, and that becomes the computational version of it. And depending on the context, all these definitions make sense. Okay. So what do we study? In this work, we consider the properties of aggregation for verifiable random functions. So let me be specific. We consider aggregating many points computed with respect to the same preimage, but different key. Okay? And we're interested in the aggregation properties also when the adversary is able to control some of the keys and compute some of the inputs. So this notion is actually very well studied for functions that are not pseudo-random but just unpredictable, which is just another way to call digital signatures. So it's a very well studied, it's a very useful notion, and this is essentially the analog of that. As a simple application, it gives you a very simple one-round distributed VRF, essentially by definition. And there are many other conceivable applications. Some of them are in the paper. Most of them are made up, but you can see you can see for yourself that is very likely to be a useful primitive. Okay, so what do we talk about in what I want to show you today? In the paper we have definitions with the aggregate version of pseudo-randomness uniqueness, and there is an additional property called aggregate binding. There is a construction based on bilinear pairings. Which is actually concretely efficient. It has a nice key homomorphic property, but the security is only proven in the random oracle model. And finally, there is a generic construction which can be based on a variety of assumptions, including the learning with errors problem, which is what I'm going to talk about today. Okay. So so what's the sort of first thought when we try to aggregate different verifiable random functions? The first thing you could do is just to hash all of the images, okay? Now, of course, this is no longer verifiable because if I have access to the root of the hash, I cannot verify it. And so that's the reason why we add batch arguments for MP, also known as bargs. In fact, we will compute two different bargs, two for reasons that will become clear later, for exactly the same statement, but the statement is that for all indices I in the leaves, there exists a tuple consisting of pi, y, and pi, where pi is a valid root to leaf path in this tree, and pi i is a valid proof under yi under the original key. Okay, this is very natural. That's the thing you would do, and we actually require the barg to be somewhere extractable, namely that there should be a target index for which, given a trapdoor, I can extract one witness for that particular index, so one such tuples. And furthermore, this index should be computationally hidden from the eyes of a distinguisher. That's the standard properties for batch arguments. And so, okay, so let's try to prove something about this construction. The first thing we want to prove is that our aggregate is computationally indistinguishable from uniform. And we want to prove this in a setting where the adversary can control, just to keep things simple, let's say all but one pre-images of the hash, right? We need at least one to be pseudo-random, otherwise there is nothing. There is no entropy left. So we want that essentially the adversary cannot bias this distribution. It's actually a priori not clear, in general probably even not true for hash functions. So our first idea is to construct something called a function binding hash. And a function binding hash it has the extra property that you can choose a node of the tree. Doesn't have to be the leaf, but can be actually any node of the tree. That you'll see why that is important. And you make the root of the tree statistically bound to that node, okay? Furthermore, of course, the node that you're targeting should be computationally hidden. Okay. So actually we show in the paper how to construct this from rate 1 fully homomorphic encryption. It's actually important to use rate 1 for technical reason I don't want to get into. But if you're familiar with the literature of somewhere statistically binding hash, is not that different from the paper of Hubecek-Wicks. But again, it requires a little bit of work. Okay. So let's pretend that we have this primitive. So what do? Well, we know that at least one of the leaves has to be pseudo-random, because it has to be honest. So we can make the hash statistically bound to that point, okay? And so that means that we can also think of the root as some sort of encryption. Let's just think really about this as an encryption of this leaf, just by the property of our hash function, okay? So now we have made progress because Y3 has entropy. So now it's sort of tempting to conclude that we can just, okay, run it through an extractor and be done. Yeah. So unfortunately, that doesn't work, and because the reason is that the adversary here can choose their functions adaptively depending on the seed of the extractor. So this just does not work. Okay. So you can cook up counterexamples, and so here is the next idea. Which we rely on the notion of compute and compare obfuscation. And the idea is actually quite simple. We add an additional layer to this tree where we feed the root of the tree through a compute and compare obfuscation program of a dummy program. Okay? So the program is doing nothing, except that in the security proof, we will switch this program from a dummy program to a decryption circuit. So the decryption circuit has hardwired the secret key, and so it can remove this extra layer of encryption and sort of output the Y3. And now we are in business because now we have a sort of an honest-to-God random thing. And the only thing left to observe is that you can use the pseudo-randomness property of compute and compare obfuscation. Now, this last property, for it to make sense, you have to open up this construction. And you'll see that it does have randomness extraction property. But this was actually already observed in these works that constructed compute and compare obfuscation. So it's not that surprising that it works. Okay, so that's how we do. This is our construction. And now we want to prove the other properties, which is the aggregate version of uniqueness. So what we want is that now, given an honestly computed aggregate, there is no adversary that can find a y star, sigma 1 star, and sigma 0 star, such that it is a valid tuple. So the two batch arguments verify against y star, and furthermore, y star is not equal to y tilde. So we don't want that. And the way we were going to prove it is by deriving a contradiction against the uniqueness of the original verifiable random function. So one of these. Okay, so let's see how we do it. Yeah. So I removed the compute and compare just to make things simple, but you can pretend that it's still there. So here we have our honestly computed tree, and recall that by the extractability property of the batch arguments, we can extract root to leaf path, but only one of them. Okay. So let's say we start with the leftmost one, and in both batch arguments. Now, if we were lucky, and I denoted this colored nodes to be the one that actually differ from the honest tree. Yeah. So we assume that they differ, so they must differ in the root. Yeah. And then it can go arbitrarily. So if we were lucky and they would differ all the way up to the leaves, then we would be done because now we can derive a contradiction against our VRFs, which are at the very bottom of this tree. But we don't have to be lucky. I mean, the adversary can do whatever he wants, doesn't have to comply with our wishes. And so let's pretend that we are not lucky, and indeed we have extracted the wrong path. And now it's a little bit tricky because you have to avoid the fact that when you're switching path, the adversary also switches the difference, right? So you sort of keep chasing infinitely. And so to avoid this, we make the deepest node of the tree to be statistically bound to the root of the hash. And this sort of allows us to go back and forth between the two barks, yeah? And so now we start extracting, let's say, a path which is in the, let's say, leftmost subtree of the deepest node that is different from the original tree. And so we do that for the first bark, and we can just look at this bark to make sure that this event keeps happening with a decent probability, and sort of we alternate. Okay, and now again we have made progress because again if this is different, that means that at least one of the two children must be different, and so we went one level below, and we can then proceed this way all the way to the leaf. In the you can make this argument rigorous, and in the analysis you can show that then indeed this eventually will allow to the leaf without the success probability dropping too much. And so, okay, the next thing would be to lock this thing and then switch. But let me not waste more of your time. I think you understood the point. Okay, so maybe as a quick bonus, although I told you I would not have discussed it, here is the construction of bilinear pairing. I don't want to say anything about it. I'll just flash it here. I mean, I guess my point is just, the point of showing this is that it's actually a very, very, very simple construction. There is all the technology that we had to use for the generic construction is not there. Nevertheless, it achieves essentially the same property. And its only caveat is that its security has to be proven in the random oracle model. But if you are sort of more applied-minded, maybe that's what you would like to use. Okay. So let me conclude. I think there are a lot of open problems. So first of all, an interesting question is actually formalizing security against a malicious aggregator. That's not something that we have thought about. In studying this property, I think it's a nice open question. I think sort of everything is open at this point in time. Find actually more application, a good question, and I think maybe a fundamental question is find construction from different computational assumptions, or better concrete efficiency in the standard model, so essentially interpolate between the two. Yeah, with that being said, I conclude and I'm happy to take questions. Thank you for your attention.
Is it possible to maybe abstract out like a randomness extraction question, which is achieved by this compute and compare obfuscation, which doesn't require, knowing other things?
Yeah, it's a very good question. I briefly thought about it, and whatever I could come up with was either trivial or impossible. So in this context, what really helps is the fact that there is a secret source of randomness that is efficiently computable if you have a trapdoor. And now if you can embed this trapdoor in your program, you can sort of clean up your source of randomness, and then you can use the extraction property. But it's very specific to this context. I'm not sure. I mean, certainly you could generalize it, but yeah, I'm not sure to make a useful generalization out of it. Thank you.
Okay, let's thank Giulio again.